In this video, we'll introduce moments and center of mass. The center of mass is the point on a thin plate that balances the shape horizontally. And that plate doesn't have to be a rectangle. It can be any shape. We're trying to find the center of mass. To start, we'll look at a simple example of a seesaw. Here we have a horizontal line. Think of this as the x-axis. And it's placed on a fulcrum. We have one mass on the left that is 2 meters away from the fulcrum, and then we have another mass on the right, 4 kilograms, that is 7 meters away from the fulcrum. The question is, will this seesaw be balanced, or is it going to tilt one way or the other? To begin with, think of this horizontal seesaw as the x-axis. If that's the x-axis, we want to label the fulcrum at 0. Then this mass on the right is located at 7, and the mass on the left would then be located at -2 on the x-axis. To determine whether or not it's balanced, we can find the moments. A moment is a measurement of a force's tendency to cause an object to rotate about a point or axis. The formula to calculate a moment is mass times its location. So the moment on the left would be the mass of 8 kilograms times its location, -2. This will give us -16. And then the moment on the right, we have its mass 4 times x, which is 7. We get 28. For the moment, let's think about the magnitude of each of those. The magnitude of the moment on the left is 16. The magnitude of the moment on the right is 28. Since the right side has a higher magnitude, it's going to tilt the seesaw down, which means the left side is going to tilt up. So in this case, this seesaw is unbalanced. The system is unbalanced. But what if we wanted to balance this seesaw? Where would the center of mass have to be? Where would we need to move the fulcrum so that the seesaw is then balanced? To do that, we will find the center of mass, x bar. To calculate that, we will find the sum of the moments and divide that by the total mass. We now have 8 times -2 plus 4 times 7 divided by the total mass, 8 plus 4. This gives us -16 plus 28 divided by 12. 12 divided by 12 is 1. So we now know where that fulcrum needs to be. We would need to move the fulcrum to 1 in order to have a balanced seesaw or a balanced system. We can double check that by recalculating the moments with the new fulcrum. The mass on the left is still 8 kilograms, but its location is now 3 meters away from the fulcrum, so we would think of that as -3. We get -24. The moment on the right side would be 4 kilograms times, it is now 6 units away, meters in this case, from the fulcrum. So the moment on the right is 24. And again, we're mostly concerned about the magnitude of those moments. Both of those being 24, we now have a balanced system with the fulcrum at 1. In this example, we want to calculate the moment M and the center of mass x bar. Up first, the moment. Remember, we add the individual masses times their location. So mass 1 is 12, it's at -3. 12 times -3. Plus, the second mass is 15, located at 2, and we have 20 located at 8. 12 times -3 plus 15 times 2 plus 20 times 8. We get 154 for the moment. And to calculate the center of mass, x bar, we take the moment that we just found and divide by the sum of the masses. That is 154 divided by 12 plus 15 plus 20. Twelve and 15 is 27 plus 20 is 47. So we have the center of mass 154 divided by 47. We can get an approximation. It looks like that is roughly 3.2. So roughly right here, you have the center of mass. Let's extend what we know about moments in the one-dimensional x-axis to the two-dimensional Cartesian plane. Let's say we have this mass m sub I, and it's located at x sub I, y sub I. We'll calculate moments similar to how we did it earlier, but now we have two of them because we want to calculate the moment about the x-axis and the moment about the y-axis. We're in two dimensions now. The moment about the x-axis will be the m, the mass, times the distance from the mass to the x-axis. In this case, y sub I. And the moment about the y-axis will be the mass, m sub I, times its distance to the y-axis, which is x sub I. If we extended this to a system and had more than just one mass, we would add them up. We would have m1 y1 plus m2 y2 and so on, and the moment about the y-axis would be m1 x1 plus m2 x2 and so on. To find the center of mass, we will find x bar, y bar, similar to how we found x bar in the one-dimensional examples. We have the sum of the moments about the y-axis divided by the total mass. That will give us x bar, and then to find y bar, we have the sum of the moments about the x-axis divided by the total mass. Let's find the moments and the center of mass for this two-dimensional system. First, the moment about the x-axis. M sub x is the sum from I equals 1 to 3 of the masses times their distance to the x-axis. The first mass we have is 5, and we're going to multiply by 1. Plus the second mass, 8, times 4. Plus the third mass, 7, times -2. Here we get the moment about the x-axis is 23. Then the moment about the y-axis. Here, m sub y is the sum from I equals 1 to 3 of the masses times their distance to the y-axis. First mass is 5, and we're going to multiply by 3. Plus the second mass, 8, times 0, plus the third mass, 7, times -5. And here we get the moment is -20. Next, we'll calculate the center of mass, x bar, y bar. To calculate x bar, we take m sub y, the moment about the y-axis, and divide it by the total mass. And y bar is mx divided by the sum of the masses. My we found to be -20. We'll divide by the sum of the masses. 5 plus 8 plus 7 is 20. And then mx we found to be 23. Divided by the sum of the masses, which is 20. So if we want that in decimal form, we'll get -1, 1.15. This is the center of mass. And we can plot that to get an idea of what it looks like. -1, 1.15 will be roughly right here. And that is our center of mass.